Good afternoon, delegations, ladies and gentlemen, and also good morning, etc., to those people who are online. My name is Dr. Craig Donlon. I work at the European Space Agency, and I'll be giving you a view from one space agency on how we can deal with the accuracy of measurements for climate. There are other space agencies who are doing the same amount of work. Right, here we go. Press this one? Yeah, green. So we have worldwide urgent priorities, which are summarized in many of the documents that you see here, and there are more. We have the Sustainable Goals of the United Nations to work with. The evidence of dealing with priorities, having to make decisions, is critical. Earth observation, EO, provides unequivocal evidence, and it provides facts that underpin many of the examples that we see in the climate reports. It's the evidence base. And it's an overwhelming evidence base because we produce so much data. I would not say it's worse or better than the in situ observations, which are equally important. It's just that we have so much more observation. And there's a reason from that. We have a beautiful view from space. We can see things that we cannot see in any other way, from the very thin atmosphere through to the complexity of the clouds and the beauty of the ocean that you see in this picture taken from the International Space Station. In terms of the missions, the satellite missions at the European Space Agency, we have a whole host that are in flight, have already flown, or are going to be flown quite soon. And we're developing a total of 82 missions at the moment. We have 15 operational in flight today. And each satellite mission carries a sensitive scientific instrument producing a scientific measurement. The currency of Earth observation is a scientific measurement. And it's our duty to make sure that we calibrate and we reference those measurements back to the SI units and provide full traceability because we overwhelm the data space. If we think about the European Union Copernicus big revolution, where we've produced a whole series of operational Earth observation satellites, today, it's the largest producer of Earth observation data in the world. We observe everything, 25 terabytes of data per day, 250 terabytes of Sentinel products disseminated by services every week. It's an enormous amount of data. So in the context of climate, it had better be right, because we have very different requirements for climate. We need much more accuracy. We're talking about 0.3 Kelvin instead of 0.03 Kelvin instead of 0.3 Kelvin. We have many more variables, as Anthony pointed out, to deal with in climate. Observations must maintain consistency over many decades, which means we have to use multiple satellites to achieve that. So a very different set of requirements here. And there have been several workshops. One was mentioned in the previous talk with the WMO. But also there were pre-COVID workshops, and here with the Committee for Earth Observation Satellites, together with the Global Intercomparison of Satellite Data, which produced a very nice report on what we need to do to improve our traceability. Because here we have multiple measurements of the atmosphere, the land, the ocean, and the cryosphere, giving that evidence base to secure the decisions made by politicians as they navigate climate mitigation. Taking the pulse of the planet is what we really are about. Now, in order to do that, in order to make a trustworthy decision, we need trustworthy observations from space. And that requires quantitative, comprehensive, accessible and usable data. And I know that in the discussions you have here, there is an element of how we actually navigate data and how we look at strengthening the interoperability of data and also the stewardship of data. The digital transition is important. But also we need to have confidence in the metrological quality of the data, and this is where we have to resort back to the basic SI units. When we're asking questions about should we build and raise the defences in the Netherlands against sea level rise, or should we raise and improve the Thames barrier, these are monumental decisions with great impact, and therefore we have to make solid decisions based on evidence. So at the European Space Agency, we have Climate-Space, which is a program which is dealing with inputs from the satellite data themselves, where we produce essential climate variables and climate data records from multiple satellite missions. That output is then used as the evidence base to support member states at the UNFCCC Paris Agreement discussions and beyond. Also to improve our modelling, they provide a baseline both retrospectively for verification of climate runs, but also initial conditions. And the same for tipping points, trends, and understanding the quality of the observations, making real measurements of our real planet Earth. And altogether, the state of the climate is delivered to WMO, to the Intergovernmental Panel on Climate Change, as a big output. And in this process, we recognize the essential role of the international system of units in providing confidence in the accuracy and global comparability of measurements. It's fundamental to what we do. And that's because we're interested in protecting our environment, global climate, and also for scientific research. So you know the core principles of metrology and the move from physically based standards to now the SI units and the constants. But how do we do this for space? We have to translate this into what we need to achieve in the space environment. And that's where we have quality assurance for Earth observation, where we're defining the measurement and the measurement function, establishing the traceability of that function from first principles, then evaluating the sources of uncertainty in the correlation tables. Where do we have an effect, and what does that effect do to our measurement? Calculating those quantities, and at the same time storing in the digital transformation, storing and making that data available to users. We have the concept of fiducial reference measurements, a tautology for the English speakers in the room. It's the reference measurement set. And those are the things that we absolutely have to have in order to make our space observations work well. They're independent, they're fully characterized and traceable ground measurements. We have many, many different activities going here. And the reason for this is, in the early days, anybody could go and buy a radiometer, for example, off the shelf, make measurements, publish a paper, and say that perhaps the European Space Agency's satellites are not working so well. And this is not a good position to be in an intergovernmental organization. And so it was our duty to educate our community so that through the peer review process, they themselves would police this environment. We know that it takes time and effort to go from the international temperature scale through to a field radiometer, but this is essential. And while it looks interesting on this slide here, the reality is more like this. And this is one comparison done at the National Physics Laboratory in Teddington this year. We've had previous examples of the same functionality with NIST in the United States. And we run these comparisons every 5 years in the laboratory. We're comparing field radiometers to reference radiant sources and secondary standards used by the field measurement teams themselves for their own calibrations. These are all double-blind tests, and they're complemented by in-the-field tests done under the same conditions. And the reports for this will be out later this year. But it's essential we do this in order to maintain the traceability of reference measurements on the ground to those in space. If we take an altimeter, which is essentially a clock in space, the nanosecond timing that we require in order to use a radar to measure the height of the ocean is critical. And then we enter the world of UTC time, or UT1 time, and we're applying the different leap seconds retrospectively to make a climate record. And so I note that in this meeting, you will be discussing those elements. It's really important for us that we have a very good implementation of time that can be applied seamlessly and with good knowledge. And in fact, there's a nice reference paper on exactly this issue that was published last year to cover that issue. It's important. The satellite in space is actually better than any measurement we could make on the ground, yet we need to do so. And when we're working in the concept of fiducial reference measurements, we have to trace everything from the position of the transponder right the way down to sea level. And at the same time, make sure that every element of that measurement is captured in an uncertainty table. We're not only doing that, but we're making sure that in the very founding principles of new satellite designs, we're implementing SI traceability for the actual build of the satellites. We've taken on board the concept of total standard uncertainty, and we're pushing back towards the manufacturers of spacecraft to actually implement pre-launch characterization and calibration in the appropriate way. And by forcing this equation, which includes the PL-CAL, the pre-launch calibration, industry has to own the responsibility for the calibration in space. No more absolute radiometric accuracy, whatever that actually means. So we're now following the BIPM GOM approach, and we're very proud to do so. We're also embedding in the very requirements that design a satellite mission the need for traceability to SI units. We're mandating the SI system as part of the satellite build. And also the need for uncertainties, and at the same time to make sure that those are delivered to users. These are very important requirements for new satellites. Oops. If I take an example here quickly of Sentinel-6, which is a joint mission between NOAA, between EUMETSAT, the European Space Agency, NASA, the European Union, and the French Space Agency, CNES. Here we're interested in measuring sea level. And sea level is a very important variable, as you all know, but none so for a politician, where 1 centimetre of sea level rise in certain countries means a relocation of up to 3 million extra people. That's an enormous obligation. You can see that the record is made up of multiple satellites, but in order to make sure that we have seamless transition between the satellites, we need to fly them very close together for up to 12 months. So some would say this is wasted opportunity. We could be making better measurements with the satellites dispersed. We have a better geographical sampling and spread. But it's essential that the record actually includes a good handover from one satellite to the other. And so we're implementing that on many of our spacecraft today. Also, we're working with the methodologies, so the uncertainty tree, starting from first principles of the measurement and breaking out all of the effects. Conceptually, it looks like this. Practically, one level looks like this. It's extremely complex, but at the same time, you learn a lot. And not only do you learn a lot, but you teach a lot. The assumptions that are embedded deep into an instrument's functionality can be unpacked, explored, and discussed through the Jacobians. It's very, very important to do that. And at the same time, it's very important to make sure it's visual so that people can grasp what is going on and get pulled into the discussion. Discussion is at the very heart of making sure we understand how to do uncertainties well. Finally, I'll leave you with one mission, and Clario was mentioned beforehand from the United States, but TRUTHS is being implemented now at the European Space Agency. It's an Earthwatch mission, it's under preparation, and this is really a standards laboratory in space, a gold standard reference to support the climate emergency. Here we're looking at climate benchmarking through an SI traceable satellite. We want to enhance the ability to look at the Earth's radiation budget, at the same time to make sure we have a standard that can be used to cross-calibrate different missions in the visible spectrum and the shortwave infrared, and also provide that SI traceability of measurements in space for the first time. So I have 2 minutes left, so I'm not doing too bad. It's a benchmark measurement, but with the characteristics of a laboratory in space. It's a very ambitious attempt to do this. It's an exciting mission, but I think it leads us into the future. If we're serious about using our space observations for climate measurements, we need to take the obligation for SI traceability extremely seriously. So at the European Space Agency, climate data records from satellites are part of our bread and butter. We are committed to deliver climate from space. And to do that, metrology is absolutely essential. It's in our blood. But it's no more so because the overwhelming volume of data we get from space means that small errors have major impact on climate time series. And if you take the example of the high latitude regions, apart from a handful of measurements in the early days from explorers, almost the entire record comes from space observations. Certainly, the spatial extent and the changes that we see in the Arctic are largely delivered from space today. So those measurements had better be right. And I can assure you, they're very, very, very good. But we're trying to embed metrology, uncertainty, traceability into all of our satellite engineering and scientific processes, in our satellite designs and our data processing, via the fiducial reference measurements for verification and validation, flying our constellations in tandem flights to understand differences, in new SI traceable satellite missions dedicated to SI traceability, and by implementing the quality assurance for Earth observation and uncertainty modeling techniques. And because of all of that, it's very easy for me to say that the European Space Agency recognizes the essential role of the international system of units in providing confidence in the accuracy and global comparability of measurements needed to protect the environment global climate studies, and scientific research. And I must add, including the use and future development of the UTC. Thank you very much for your time.